Hi. Today we're going to talk about an example of a chi-square test. And then this particular set of data, we're going to be able to use a different test to make some conclusions about at the end. It's going to be kind of surprising. Okay, so let's explain the meaning of this data first. You'll notice this categorical variable here on the left called patient status, alive or dead. And the categorical variable on the top is pet ownership, whether or not this person's owned a pet. So let me just read a little background. Psychological and social factors can influence survival of patients with serious diseases. So, mind over matter, I guess. One study examined the relationship between survival of patients with coronary heart disease and pet ownership. Each of 92 patients were classifying as having one pet or not by whether they survived for 1 year after being diagnosed or not. So, for example, this 28 means that there were 28 patients among the 92 who were alive after 1 year but did not own a pet. Okay. This 50 means that at the end of a year, there were 50 patients who had been diagnosed with coronary heart disease who owned a pet and they were still alive. Okay. And then if we look at the status down on the bottom, this is maybe what the researcher might suspect. If we look, for example, at this 3, it's saying that there were 3 pet patients who owned a pet but did not make it a year, whereas over here we had 11 patients who did not own a pet who did not live out the year. And so you'll notice comparatively 11 compared to 28 and 3 to 50 that those are different proportions. That's a big hint as to what other tests we might be able to do later on. Okay, 2 proportionality tests we'll talk about. All right, so first thing to consider in this case was that this isn't really an experiment. This was an observational study. We started with people who had these diseases, and then we also asked them after the fact about pet ownership. So I don't know how you would design this as an experiment. That'd be a little tricky, but okay. So the researchers thought that having a pet might improve survival. So pet ownership is the explanatory variable. So let's talk about a test. So a hypothesis might be that there is a relationship between the patient status, I'll call that the patient status, and pet ownership. And this is HO would be there is not a relationship between those 2 variables. In other words, HO is saying these 2 things are independent of each other. Okay, and then HA is going to be that there is a relationship between PS and PO. All right. So usually in these things, it's it's HO which indicates independence, versus HA which indicates dependence. Okay. All right. So this is a chi-square test. We should check our assumptions. Number 1 are all our data in counts, and they are. Number 2 is the population of all people who have coronary heart disease greater than 10 times our sample size, which in this case was 91. I'm going to say yes, it is. Okay. We're going to need to check that all expected counts are greater than or equal to 5. Okay. Sometimes we say no more than 20% of them could be less than 5. So in this case, none of them can be less than 5 because there's only 4 different categories that we could be in. And then lastly, we're supposed to have an SRS, and that might be where you consider this assumption not satisfied. So for the time being, we're going to assume that it was and proceed, but we'll go from there. Okay, so now what we want to do is perform the chi-square test. Okay, so before you can do the chi-square test, we have all our data here in counts, and what we're going to need to do next is get our expected value. So these are our observed counts here. So now we need to get expected. Okay, so to get expected, here's what we learned about. We had a nice formula for 2-way tables. No, yes. Here's our table. And what it was to get the numbers, for example, if you want the number that goes here, you take the row total times the column total over the table total. So T stands for total here. So for example, this matches or corresponds with the 28. So the column that 28 is in, which has a column total of 39. The row that it's in, if we add this way, has a row total of 78. And then the table total is 91. So we have right here 39 times 78 over 91. We type that in a calculator, we get about 33.42. So that's going to go in here. So now you have to redo that process. So for example, if you want to get what goes here, in that position, that corresponds with the 3. So that column total is 53. That row total is 14. So you're going to have to get this number. You're going to have to do 14 times 53 over 91. And then you need to proceed for all the other things. So let me show you can speed this up a little bit with your calculator. Okay. So we're going to go to our calculators for a minute. Just to remind you, there is a chi-square test in the calculator. So if you go to stat, you go up to tests, you go up to, here we are, letter C. There's the chi-square test. And it'll say observed and expected. Your observed is a matrix A. And the expected matrix goes in B. So we need to put those things in. Actually, we only need to put in observed. That's sort of a nice thing. I'll show you that now. So here's how we do it. We're going to do second quit and get out of here. We're going to do second matrix, which is second the X inverse key. And here's the big screen. You can watch it. We're going to go over to edit. And our matrix did have 2 rows and 2 columns. So this looks good. And all we're going to do now is go to our matrix and type in these observed counts, 28, 50, 11, and 3. So that's what I'm going to do now. So 28, enter, 50, enter, 11, enter, and 3, enter. So there you go. This is our matrix A. Now we should make sure everything's okay. So do second quit again. Go back to matrix, do second X inverse for the matrix, and just hit enter while it says names here. And then take a look at it. Enter again. There's the matrix. That's my observed count. So here we go. We'll go back to stat. We'll go over to tests, and we'll go up to the chi-square test. There it is. We'll hit enter. Observed is A. Now, the expected matrix is B. We had started to build that here. We had this one number of 33.42 right there. We were about to calculate this number. We'd have to do it 2 more times. And what I'm telling you is that the calculator will do all that for you. You need to tell it what the expected matrix is. We go to calculate, hit enter, and here we go. So we got a chi-squared test statistic of 8.85 and a p-value of about 0.003. Go to the page and make a note of that. So chi-squared was about 8.5. The p-value was low at 0.003 approximately. That gives us enough evidence. So what does this tell us? Our p-value is, notice it's less than alpha equals 0.05. So that implies our chi-squared test statistic is significant. Okay. And we can reject HO in favor of HA. Okay, in the context of this problem, what that seems to mean is that there is a relationship. So in other words, pet ownership and the survival status, the patient's survival status after 1 year are dependent. Okay. But there is a little bit of a limitation there. The limitation is you don't really know the direction of the relationship. Now, if we look at the data, it seems to be, if we compare these 2 columns, for example, if you look at this, the number of patients that are alive after 1 year and had a pet is 50, while the number of patients who are dead after 1 year and had a pet is only 3. Then if we look at this other column, we see sort of a different relationship here. It looks like the number of patients who were still alive who were alive after a year but didn't have a pet was 28, but the number of patients who were dead after a year didn't have a pet is 11. So this researcher might be suspecting, hey, I think that this pet is bringing some happiness to the person's life and allowing them to, making them want to live longer. And maybe that's the case. But this test does not tell us that. This test just says that these 2 variables are dependent somehow, that they're affecting each other. That's sort of a limitation of a chi-square test. Now, before I leave the chi-square test, I just want to show you one of the neat things. You remember we started to calculate our our expected matrix here, if you go to the calculator now and you go to matrix, you'll notice matrix B is there. And if you hit enter on it, oh, hold on a second. Something happened there to my calculator. Oh, there it is. A little bit of a glitch. But you can see there's that 33.06 number that we had calculated before, just to remind you. Or 33.042. Now, I did a little bit of rounding, so that's probably what happened. But you can see the expected matrix comes up. So the calculator automatically computes that for you. Sort of nice to know. Okay? All right. So there it is. And if you hit the right arrow, you can scroll right and look through it. Okay. Let's take a look at this data again. Let's think about what we're interested in here. This researcher believes that pet ownership might have an effect on how long someone survives, and they seem to, the way the problems were, they seem to imply that this person might be more likely to live for a year or more if they owned a pet. So let's think about this from a proportion point of view. I'm going to say let P of, we'll call it P-O, we'll call it P, yes, we'll say it that way, will be the proportion of pet owners, right, who said yes, who actually own a pet, who are alive after 1 year. Okay? And then we're going to let Pn, P no, be the proportion of pet owners who said no, they don't own a pet, who are alive after 1 year. Okay? So I've restated this thing I'm interested in terms of proportions. Now, what would our hypotheses look like? Well, if owning a pet has no difference on how likely you are to survive when you're faced with coronary heart disease or some other condition, then these two proportions should be equal. P yes should equal P no. All right? Now, if this researcher, the way they're implying things, they seem to be saying that they think that the people who are going to stay alive after a year would be, the proportion of people who stay alive after a year would be greater if they owned a pet versus the group of people that don't own a pet. Okay, so this is one way to write the hypothesis. Another way to write it might be P yes minus P no equals 0 versus P yes minus P no. Now we would expect this proportion to be higher, so that's going to be greater than 0. Okay. So you'll notice what's sort of nice here is that if we do a hypothesis test with these hypotheses, when we're done, we'll have a direction of the relationship. Now, for the time being, there are many checks for assumptions when you do a two-proportion z-test, which is what this is. So you have to check that they're both SRSs. You have to check that both populations, the population of people who have pets and the population of people who don't have pets, is greater than 10 times the sample size, those respective sample sizes. And then you also check for normality. And for normality, you got to do that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Now, like I said, I'm not going to check all these. You have to do this for both groups. You got to do this for the yes group and the no group. You got to make sure that both of those distributions of proportions are greater than or equal to, well, both of them are normally distributed. The only way to check that is to make sure that these two conditions work for both. All right, so we're going to move forward assuming they have, and I'm actually going to use the calculator to calculate things. Just so you remember what everything is here. Hold on a second. The z-test statistic for difference in proportions looks like this. Like that minus that minus 0 over standard deviation. And don't forget, you got to use p hat combined in a problem like this. 1 over n1 plus 1 over n2. Actually, I should be careful. Just so you know, the 1 goes with the yes group, and this goes to the no group. The p hat combined, the reason we're doing that is because in the hypothesis test, you're assuming HO is true. And if HO is true, then p hat combined just means we would add the two proportions together. Well, not really add it. Let me show you what you would do here. So look at our information that we have. Here it is. So this column total is 39. and this column total is 53. So the p-hat for yes would be 50 divided by 53, and the p-hat for no would be 28 divided by 39. So those are two separate proportions. So what we would do is we put the people who were alive after a year. Here's this number is for no pets. These people had pets over the total people that were in the study, which is going to be 39 plus 53 or 91. Okay, and then we can divide that and get a p-hat combined. And we're getting a number of around, looks like about 0.86. Okay, so let's actually go do that two proportions z-test. You can do this pretty quickly in the calculator. We go to stat, go over to tests, we go down here, number 6, it's the two proportion z-test. There it is. We hit enter. And x1 would be the number of successes in the first group. So that's going to be 28. And n1 is the size of that group. So these are the people with no pets. There's 39 of those in the study. And then x2 is the number of people who survived in the other group. Well, 50 of them did out of 53 in the group that had pets. Now, here's what happens. If you did this not equal to, then you're not taking advantage of the two proportion z-test. As a matter of fact, if we calculate that real quick, watch what happens here. You get there's that p-value, 0.003, really. It's the same p-value we had before. We shouldn't be surprised at that because the chi-square test really tells you the same thing. Are these proportions different or not? Okay? So let's do the one sample. Let's do the directional test. So we'll go to number 6. And the only thing we'll change here is we think that P1 is going to be bigger than P2. So here we go, enter, calculate. And, oops, I did it the wrong order. Sorry about that. Hold on a minute. We did this, because I typed it in the opposite order. So we need to go to this. There we go. That's what we want. So we calculate. And we get an extremely small p-value. Oh, I hit the button wrong. I pressed the wrong button. Sorry about that. But what you'll end up getting is the p-value is equal to 0.0015, which is half of what it used to be. That's because you're switching to a one-sided test. So let me just say this. What you can do is if you have a 2-by-2 table, then you always have the ability to do this test two ways. You can do a chi-squared test for independence, but that doesn't give you the directional relationship, versus you can do a two-proportion z-test. Just make sure we get that thing in the calculator one more time. Sorry about that. Stat, tests, number 6. Let's go down here. And, oh, this would happen. I lost my denominator. So that was 39. That was giving me that error domain. That was 53. Let's go to calculate and hit enter. And there it is, that really small p-value, about 0.015. Okay? Thanks for watching.